All right, so in this lesson, we're going to learn more on NoSQL databases. NoSQL stands for not only SQL. So we saw from the last lesson that RDBMS has been there since 1969, and traditional RDBMS-based data storage emphasize optimal storage cost of the data. So most important criteria in an RDBMS was, how do you ensure that the data that you're storing is really optimized for storage so that you're not duplicating the data, you're not having data redundancy of any sort. All those things were eliminated by establishing relationship, creating multiple tables. So that is how we solved that problem. However, what happened over the years was storage costs started dropping dramatically in the last few decades. Here is the chart that shows how the hard drive cost has dropped dramatically over the last 35 years. And so all this complex way of building relationships and ensuring that the data is no longer redundant was not truly a big win for the business. Because what was more important was the retrieval cost. How quickly can you get the data out? That was becoming more important. And again, I touched on this topic a little bit earlier as well. So you go to Google and then you search for a particular keyword. And when you get the results, if you're waiting for 3 to 4 minutes to get the result, nobody will be there Googling, right? So we want those results in a fraction of a second. So that was more important than storing it optimally. So businesses started changing based on availability of different resources and the cost of different resources. So no longer storing data optimally was the criteria for many of the businesses. So before we proceed further, however, let's understand this CAP or this Brewer theorem. So it's basically based on you pick two option. I don't know how many of you go to Panera. So you have, in the Panera, you have all these menu items where you can pick two and, and it costs the same. So it's something similar to that here. So you have three things on the menu: consistency, availability, and partition tolerance. And this comes from theoretical computer science, where as per this theorem, any distributed data store cannot have all three. Just like the way you cannot really buy all three for, for $7.99 or whatever that cost of that you pick two is. You can't buy everything that they have on the menu. Similarly here, you cannot have all three of them. You can only pick two of them. So either you can pick consistency and availability, or you can pick consistency and partition tolerance, or you can pick availability and partition tolerance, but you cannot have all three of them. That's what this theorem states. So what exactly is consistency now? Again, I've talked about that in the previous lesson. That is the foundation of a database, right? The ACID, C stands for consistency only in the ACID properties. So in a system containing replicas, all the replicas must contain all updates before providing access to the data. Hence, any kind of concurrency control techniques like locks are applied to ensure that the database is consistent. And when it comes to availability for a distributed system, again, to be continually available, every request received by a node in the system must result in a response. An available system must have replicas because failures on the server side may occur. So again, availability is kind of a simple concept to understand. I think everybody gets that, I'm thinking. So how many of you have ever had a situation where Google servers are down and you can't do a search? Has it ever happened? At least in my experience, I've never come across that situation. Their systems are always up and running. It has happened in a banking system, however, when I go to a bank and sometimes I'll get this, oh, system is down, please come after a few hours or something like that. That I've seen in a banking system, but I've never really seen such a thing with a Facebook or Google or Twitter. Never even heard of, actually. So anyway, that is availability. Availability is how much is the system available. And again, these are all distributed systems. You're not just having one server serving us, right? So we will have hundreds and thousands of servers serving millions of people. We obviously cannot have just one server doing that, and we'll have a lot of many different servers. But the point is that it's always available. So that is availability. And next is a partition tolerance. So if the replicas are on different nodes, the system must continue to operate even in the presence of a network partition. So this also happens a whole ton. System down, networks down, all those things are pretty common because something will fail all the time. When you have thousands of servers and many different networks connecting many different computers, you'll have something failing all the time. So the partition tolerance tells us that just because it got partitioned, the replicas are no longer connected to each other, then also the system should still be working, whatever the customers, whichever clients are connecting to whichever part of the divided partition network, they're still getting served from that respective partition nodes itself. Those nodes are still up and running and they're still serving even though there is a disconnect between them. So as I said, the CAP theorem says you can only get two of them. You can't get all three. So you have to sacrifice one to get another. So let's understand this consistency example a little bit. So let's say that you have all these distributed databases which are spanning multiple. So let's say that this is a big bank, okay? And this bank is like, this Visa or MasterCard or whatever, where they have all their as you know, most of the banks actually provide you with those kind of cards. And now if you have an account, then that account is obviously replicated and it is available across the many different servers that are out there throughout the world. So let's say that, again, it's a hypothetical scenario. Let's say that you have account, the bank accounts in Detroit, and you're deducting $200 from your account in Detroit. And the next instant, if somebody from Tokyo is trying to read your account and find out how much money you're having in your account at that instant of time, it should still show them $300, right? It should still show this. It's not going to show whatever you had previously, which must be 500 because your now present account value is 300. So that means before this update happened, it was 500. But once this transaction finishes, if it is showing 300 on this Detroit-based server, then a Tokyo-based server, if a client connects to the Tokyo-based server and tries to find out what's your account balance, after this transaction finishes, the next instant of time, it's in a fraction of a second, if somebody goes and tries to find what is your amount, it should show them 300 only and not 500, even though they are they are all different continents altogether, but it should still show 300. At least that is the expectation in the banking system. You all agree? That's expectation in the banking system. We can't really have some inconsistent data. Once if you remove some amount here, then that should show up in whichever place, wherever you're trying to access that account, from whichever replicated database that you're looking into, it should still show the exact same thing. And again, as I said previously, that is the guarantee of databases. RDBMS, that guarantee is there for us. If this transaction successfully finished, then yes, it will show that no matter what. So again, these are all connected through these networks. I'm showing the network here with this wiring. So that just shows that these are all connected through the network. And this is the consistency, 100% consistency example. So again, RDBMS obviously wanted this. They bank on this consistency because that is a guarantee that they give us. So this is a consistency example. Now when it comes to partition tolerance, so let's say that there is a partition here happened. This network failed. And although this updates that were happening here was always getting replicated, this update that previously in this previous slide, we had an update and that update was getting replicated. That's the whole point of showing this connection, right? So as soon as this update happens, that update is propagated to all of these at the same instant of time. That is the whole guarantee that we have. Now, in the next one, what is happening is that we have a network failure. Because of which what happened, the replicated database are partitioned now. In this case, what happens is the banks typically let you do a read on it, because read is like you're simply going to read what is the value that you're having in this account, which is $300, that you can read. But then if you try to update, then it will say, sorry, I can't let you update now because there's a partition that has happened here, and we can't propagate that update to all the other nodes. And so it will come back and say, system down. I can only let you read, but I can't let you update anything. So something like that they will do. So partition tolerance, although in this case, it is still going to let them read though. I mean, the clients can still connect to this node, and the clients here can also connect to this node. And they can query the data, they can read the data. All those things are perfectly fine. So it is still partition tolerant, even though it actually broke here. It is still serving. It's not bringing the whole system down, saying, "Oh, I can't do anything right now. We are totally out, and we're out of business for now. We can't help you." That they won't say. They're still running the show, but with limited capabilities. They're still running the show. So this is partition tolerance example. And now when it comes to the database, now based on this CAP theorem or Brewer theorem that we just now saw, out of the three properties, which one do you think they chose? Well, obviously consistency is their foundation, so they can't obviously throw that out of the window. So they picked up consistency, and they had a choice between partition tolerance and availability, and they chose the partition tolerance, because obviously availability, you can only pick one of them. So they picked up to partition tolerance and consistency, and obviously they let go of the availability. Means to say that the system won't be available 100% of the time. That is why you see a lot of the times that you see is that banking systems are down. Every now and then system is down, come back later, it's not available because they're trying to be consistent. They're trying to enforce this consistency across all their data. And that is why they have sacrificed availability, because that is, as I said, you can't get all three of them. Okay. So next, when it came to the new age companies, like all these social media and search companies and all of them, their priorities were obviously different. They were not truly interested in that high degree of consistency. Again, I kind of touched on this part a little bit earlier as well. So if you went on Google and search for a document, and if it is still indexing, we saw that in Solr indexes, that when you added a new document, and that new document is there in the master Solr, and it is still not yet replicated to the rest of the Solr nodes, and it's okay with them. I mean, it will eventually get replicated, and all those other nodes, slave nodes, also will start bringing that new document that got added into the master. But at some point of time, when somebody goes and searches for that document in the master, that document pops up because it is already there in that particular index, but it is still not there in the slaves. So if somebody tries to go and search for that same document in one of the slaves, that document is yet to be added into their indexes, so that document doesn't show up. So what do we have here? Inconsistencies, because it shows up in some search results. On one of the nodes, it's showing up, and in another node, it doesn't show up. So there is inconsistency, and they were okay with that. For the large extent, they were fine. Okay, fine, it's not showing up right now, but eventually it will show up. After some time, it will all be good, and we're not worried about it. So that was their argument. But what is that they always wanted, though? They wanted availability for sure. They don't want to be showing to the people, hey, our Google server is down now. Please come later and search for your documents. That they wanted availability as their topmost priority. So anybody, anytime they can go search. But yeah, I mean, you may not be getting the same set of documents. Two different people in two different parts of the world may not be getting the exact same search results for a particular keyword. Do you even know that? Nobody even knows that, actually, that something like this is happening. Only people at Google will actually know that this is what is happening, right? That is pretty much how it is. And the same thing true with the Facebook. You made a post and one of your friends liked it or whatever. And if others don't see that like immediately, as soon as that person liked and they can't see it, what's the big deal, right? It's no big deal actually. And they will eventually see that after a couple of hours or tomorrow or whatever. And typically it is within a couple of hours, everything will be sorted out and everything will be replicated. But for that fraction of a time when it is still working on it, it will be inconsistent. Things will be inconsistent. And the new age companies, the social media companies, they were perfectly fine with that. They really didn't have a problem. So they threw consistency out of the window and they kept partition tolerance and availability. And then they built their system around that. Okay. So while ACID is extremely important for databases, there is a new set of properties that we had for these new age type of solutions, which was called BASE. So BASE stands for basic availability, means to say that it's always available. Something will be working all the time, okay? May not be, sometimes some features might not work. Some features may be not there yet, or temporarily it is down or whatever, but it's available as the basic stuff is always available. So that is the primary criteria when it came to these kind of solutions. So basic availability and soft state and eventual consistency. So while the consistency was not very strong, it's going to be eventually consistent. Everything will be fine after some time. Just give it a couple of hours or one day or whatever, but everything will be eventually sorted out. The indexes will be updated and everything will be sorted out. That's all that they wanted. So that's why it is eventual consistency and soft state. Soft state is basically what it means to say is that you didn't do anything to that, but automatically it will update itself. So that is the kind of a thing which is, was not at all acceptable in RDBMS. If there is a state change, that is because of something that happened. Like the customer came in, he did something and something happened, and that's why the state changed. And that state changed across the board for all the replicas at once. But that's not how it is here. It only changed in one of the replicas, that change happened. And then in all the other replicas, they're all sitting with the old stale state itself. And that is being served to the clients who are connecting to those replicas. And then finally, when it is getting propagated, when the change is getting propagated, then eventually all those replicas are also getting updated. And that update is because of nobody interfering, but it is because it is getting propagated. So that is the soft state scenario. And eventual consistency is basically, it will eventually be consistent. So these were the properties for the new age solutions that we have. And of course, ACID, you already know that. Not going to go over those things again. That's the whole idea. I made that other video, actually. So in the contemporary solutions that we have, the main innovations that they brought up was MapReduce on distributed file system and NoSQL databases. So that's when NoSQL databases emerged in the industry in the last decade and little over a decade, actually. And of course, the main message with this new way of doing things is different approaches to data storage and processing. The traditional approach for storing data and processing data was not working out. So they wanted a different way of doing things. If you're creating your CV and if you don't know SQL, then doesn't matter. Just simply say that you're a NoSQL expert. Do you think that this is really true? So you don't know SQL, so you can say that you're a NoSQL expert. Not really, though. So that's, although it is tempting to say that, but in the real world, it's NoSQL actually stands for not only SQL. That's why I was telling you in the last couple of classes that SQL is one of the topmost skills that every single person is expecting. So you can't escape. Even in a NoSQL database, you're running SQL queries only, except what is it you're not doing then? So the ones that I did not emphasize that you should learn is the one that is probably not so much required, and that is joining. Joining tables, we have thrown that almost out of the window these days. We don't want to join tables because joining tables will almost bring the whole thing to a stall because of the way things are stored now. I mean, joins are perfect and they are extremely efficient in RDBMS because you build relationships, you have the foreign key, primary key relationship built in, and indexes are all built in for that. So it's perfect in case of an RDBMS. But however, joins are absolutely no in case of NoSQL databases because it's very, very painful to get any join up and running. But simple SQL queries like select star from a particular table, where with a where clause, all those things you have to know because NoSQL is also based on most of the NoSQL databases allow you to run simple SQL queries actually. So that's why it's extremely important to learn those basic SQL concepts of order by, where clauses, having clauses. Those are the ones that are absolutely required. But you're relieved of joining multiple tables though. That part is not required anymore. And then schemaless, you don't have to have a schema. In many of the NoSQL databases, schema is also not required. You don't even have to figure out, okay, what kind of columns that I'm going to have, what kind of table I'm going to create. That is also not required in some of the NoSQL databases. You can simply store data as is, where is. Simply take the data, put it in there, and it is there. That's it. But that was absolutely not possible in an RDBMS because first thing before you even put one single record in any of the databases, in any of the tables, the first thing that we all sat and did for several days and sometimes even months is create the ERD diagram. We used to have several different meetings. Okay, which table, how many columns, what relationship should we bring? And all those, that ERD diagram that I just showed you previously, to come to that understanding, okay, this is our ERD diagram that we are going to have. We used to take several weeks, if not months. I mean, sometimes even months actually. And then we used to finalize the ERD diagram. And after the ERD diagram is created and after all the tables are created, then we were ready to start taking data to insert them into the various different tables. But with NoSQL, that is again thrown out of the window. Very first day, we take the data, store it. That's it. Very first day, very first instance, we'll just store the data. And then, of course, horizontal scalability, we talked about that, and simple API. Simple API is something where it is not complex. Nobody wants complexity anymore, right? So we just want, again, when it comes to Facebook updates, you're just doing one update, that's it. And then when it comes to Google search queries, you're just doing some search and getting some results. So that's pretty much, in fact, you're not even doing any updates on Google servers, actually. Google is doing all that indexing and all you're doing is just searching, reading their indexes. That's pretty much it. So all of those things are simple APIs, simple queries. And some of the implementations techniques that they landed up using for getting this done was key value store, a simple key value store. There's a key, there's a value, just store it. That's it. There is no relationship between various different things. If you want to retrieve that back again, use that key, get that value back. So it's a massive key value store. And then a document store. You have a document, just store it as is. And then again, we saw with the Solar how easy it was. And then row column store. Simply store the entire row or simply store the entire column and then get me back the entire column based on a key again. And then there are also in-memory data structures. So these are the various different techniques that came out as alternative solutions. So the main advantages of these simple operations are scalability, high scalability. You can have a large number of data stored because all we are doing is a simple key lookups and then reads and writes of one or very small number of records. You're not doing a whole lot of connected things in this kind of system. There is no several entities and you writing one record in this table, another record in that table, another record in some other table. No, it's very simple. Just one record here or a couple of records there, and that's it. There is no relationship between tables and all those things are not there. And then complex joins of tables are totally eliminated. Complex ERD is no longer required. And flexibility on the data structure. Again, as I said, you don't even have to have a schema ready for storing any of your data. So what are the main disadvantages then using this approach? Well, data is no longer stored optimally. Many redundancies, consistency issues are there. And if you're not careful, they might actually come and bite you. if you're not careful with your consistency issues handled properly, then it might actually have some serious consequences. And then NoSQL databases are all differently implemented. NoSQL databases are alike. Unlike in case of RDBMS, all of them, like whether it is DB2 or Oracle or MySQL, doesn't matter. It all follow the exact same way of doing things. Like create statement of a table runs exactly the same everywhere. You once almost, at least almost, it runs exactly the same. There will be some small tweaks here and there between the databases because of some new features that they would have added specifically for their database. But for the most part, a create table that you create on one database will work exactly the same in another database. And there were some standards. ANSI SQL, they brought out ANSI SQL. So that same SQL that runs in one will also run in another. So all those standards were implemented. So it was actually very nice. When you are working with RDBMS, you don't have a lot of surprises. But that is no longer there in all these different solutions that are there in the market today. Each one of them have their own ways of solving the problem. It's more like, as I was mentioning earlier, Google came up with that MapReduce way of doing things. And they said, inside Google, this is what we guys are doing. So if you guys want, you also can do the same thing. And then Facebook came up with, okay, guys, we are doing slightly differently. We decided this way because this is what we found as very effective. And this is what we are using in our company. And if you guys want to do the same thing, you can do it. We have made that open source. So you can take that and do it. So that is how all these solutions came into the market, actually. Every company, they did something in their own thing, and they eventually made them open source and said, okay, you can use it if you want to. But then there is absolutely no standard between them. They just did what worked for them. And if that same thing works for you, good, use it. That's pretty much it. And then transaction management, as I mentioned in the previous lesson, what a transaction is, that is not even there in some of the cases. There's no concept of transaction anymore. And even if it is implemented, it is less rigorous, not like a RDBMS transaction where it 100% works and you can roll back, you can commit, you can do checkpoints, all those various different options that you have in an RDBMS, that is not there anymore, actually. And the queries which are spanning multiple entities is almost impossible. And in some cases, it is highly inefficient. It takes several hours before you can get your answers back. So some of the very nice things that we had in RDBMS were thrown out of the window, like variety of RDBMS indexing techniques, RDBMS query optimizations, RDBMS storage optimizations. All this they were like, okay, we don't want these things. So again, most of the vendors give us various different solutions for SQL, NoSQL, all kinds of things. Now, what is happening now is, okay, everybody's saying, hey, we will give you whichever solution that you're looking for. We have a lot of solutions and we have many different tools in our toolbox. And of course, we know that some places you have to use a spanner, some places you have to use a screwdriver, and sometimes a sledgehammer. So we have all kinds of tools. You pick whichever you want for whatever you're trying to solve, instead of using the same solution for every problem. As I said, RDBMS was the only solution we had for several decades, and we didn't have an alternative, actually. But now we have an alternative. And with the GCP, Google Cloud Platform, they are having all of these various different solutions in which Datastore is a NoSQL document store, semi-structured application data, durable key value data. And then when it comes to Google Big Data, this is also NoSQL wide column. And then this is mainly meant for heavy read-write events, analytical data, so can be used for IoT data and things like that. And then we have already played around with this cloud storage. All of you put your stuff on the cloud storage for your CSV file, XML files, whatever. So that is a blob store. So it is structured, unstructured, semi-structured, all kinds of things it will store. So images, large media files, and backups for all those things. This is the most optimal use case for it. And then they also have Cloud SQL, which we again played around with. We put up our own MySQL and stuff like that. So this is pure RDBMS at this point. So this best use case is web frameworks, existing applications, user credential, customer order. So when it comes to e-commerce, RDBMS is the best. So for banking applications, insurance applications, RDBMS is the best for all of those situations, actually. And then they also have this Cloud Spanner, which is also relational. Again, here you see that these are NoSQL and these are relational. And they've also given the use cases, for which use case, which solution you might want to consider and things like that. So this particular website actually has a DB Engines ranking dynamically shown. So it keeps changing all the time, actually. So on the top, you have all these relational. So that is still number one, as I was mentioning. It's not that everybody checked out the RDBMS and no more going to use. That's not true. So you see, it is still number one. Oracle is still number one. MySQL is number two. Then comes the Microsoft SQL Server, and then PostgreSQL. So all relational are actually right on the top itself. And then we have this key value store from Redis and Elasticsearch, which is a search engine. I was talking about Elasticsearch, which is a cousin of Solr. And Solr is here all the way in the bottom, which is a search engine. And then we have SQLite, which is embedded data store, which is also relational. And then Cassandra is a wide column. And of course, there are many other relational, including Microsoft Access as well. But this gives you some idea. Neo4j is a graph. So each one of them are various techniques that they use to store data.